Welcome. Here we are going to discuss about UV visible spectra and the terms involved in the UV visible spectroscopy. Before going to the UV visible spectra or terms involved in the UV visible spectroscopy, we should have knowledge about the UV visible spectroscopy, UV visible spectrophotometer, and theory of electronic transmission. The analytical technique which is used to analyze the sample based on its interaction with the UV visible radiation is called as a UV visible spectroscopy or UV visible spectrophotometer. While the instrument which is used to analyze the sample based on its interaction with the UV visible radiation will be called as a UV visible spectrophotometer. This UV visible spectrophotometer works on the principle of Beer's law and theory of electronic transition. Beer's law deals with the concentration of the medium, and it states that the absorption of UV visible light by a media is directly proportional to the concentration of analyte in that media. While in case of theory of electronic transition, whenever the analyte absorbs the UV visible radiation, then this absorption will lead to the excitation of electron from ground state energy level to the excited state energy level. In case of organic molecule, the bonding molecular orbital, non-bonding orbital will be considered as ground state energy level, while anti-bonding orbital will be considered as excited state energy level. So whenever the electron absorb the UV visible radiation, or the molecule will absorb the UV visible radiation, and it leads to the excitation of electron from bonding or non-bonding orbital to the anti-bonding orbital. This will be called as a theory of electronic transition. Now, whenever the sample absorbs the UV visible radiation and it carries out the electronic transition, the data of absorption obtained with respect to the wavelength is formulated in the form of a graph. In short, the analytical data obtained from the UV visible spectrophotometer is converted in a graphical form, and that graphical form will be called as a UV visible spectra. This UV visible spectra is obtained due to the excitation of electron from bonding or non-bonding orbital to the anti-bonding orbital, and this excitation property depends on the structure of the analyte. So this is the sample UV visible spectra. This UV visible spectra belongs to the isotope. So UV visible spectra is a graph in which y-axis belongs to the absorbance or percent transmittance, while x-axis belongs to the wavelength in nanometer. So if we consider the isoprene, it will give us two important properties. That means the graph will give us two important properties. First is the lambda max. So in case of the isoprene, lambda max is 222 nanometer, and this lambda max is also called as a maximum absorption wavelength. So the lambda max is the characteristic property of a specific molecule, and it depends on the structure of the molecule and the atoms involved in the structure formation. With this, it will give us the second important parameter, that is the molar extinction coefficient epsilon. So this molar extinction coefficient is the absorptivity of specific analyte for a solution having concentration 1 molar and path length 1 centimeter. In short, UV visible spectra is a graph of absorption or percent transmittance on y-axis, while wavelength in nanometer on x-axis. It will give us information of lambda max, which is also called as a maximum absorption wavelength, which is a characteristic property of the specific molecule, and it depends on the structure of analyte. With that, we will have information about the molar extinction coefficient. Now, we will see the different terms involved in the UV visible spectroscopy. Chromophore. Chromophore is a covalently bonded group of atoms. This chromophore consisting of double bond or triple bond, and due to this it is having ability to absorb the UV visible radiation, and it leads to the excitation of electron from ground state to the excited state. Example of chromophore is carbon bonded to carbon by double bond or triple bond. That means any molecule which consisting of carbon bonded to bond to this another carbon by either double bond or triple bond. A molecule that consisting of carbon bonded to oxygen by double bond, or a molecule that may be consisting of carbon bonded to nitrogen by double bond or triple bond. A molecule like benzene, molecule like butadiene are the examples of chromophore. Auxochrome. Auxochrome is a atom bonded to chromophore, or a group of atoms which are bonded to each other by a saturated bond, covalent bond. So it is not absorbing the UV visible light directly, but when this auxochrome attached to the chromophore, this auxochrome is responsible for change in the wavelength of absorption. That means it shifts the lambda max either towards longer wavelength region or towards shorter wavelength region. Example of auxochrome is nothing but OH attached to the chromophore, OCH3 attached to the chromophore, NH2 attached to the chromophore, halogen attached to the chromophore, or any other alkyl group attached to the chromophore. Okay. Bathochromic shift. So there are shift and the effects. First is the bathochromic shift. Bathochromic shift is also called as a error shift. Whenever there is a shift in the lambda max towards the longer wavelength region, it is called as a bathochromic shift. As the shift of wavelength is towards the infrared region, towards the longer wavelength, hence it is also called as a red shift. Here we will discuss about the example, which is the paranitrophenol. The paranitrophenol is having lambda max around 255 nanometer, but same paranitrophenol in alkaline medium will show lambda max shifted toward the longer wavelength region, and that will be having value 265 nanometer. It is due to the formation of phenoxide anion. This phenoxide anion will increase the conjugation effect in the paranitrophenol molecule, and hence it will have bathochromic shift. Next is the hypsochromic shift. Here the lambda max shift towards the shorter wavelength region. As the shift is towards the ultraviolet region. Hence, it is also called as a blue shift. Suppose aniline. Aniline is having lambda max around 285 nanometer. While in acidic solution, this will show lambda max which will shift towards the shorter wavelength region showing 265 nanometer. It is due to the formation of quaternary ammonium cation. Now, due to the formation of this quaternary ammonium cation, the lone pair of nitrogen is not available for the conjugation. So conjugation effect is lower in this case and the lambda max will shift towards the shorter wavelength region. Then effects. First is the hyperchromic effect. Whenever there is increase in the absorption intensity, that is the molar extinction coefficient, it will be called as a hyperchromic shift. Hyperchromic shift is mainly due to the solvent effect or it may be due to the oxychrome. For example, pyridine, it is having epsilon value around 2759. When in this pyridine, the oxychrome is attached like OCH3, methoxy, then epsilon value will increase to 3560. So there is an increase in the absorption intensity due to attaching the pyridine with OCH3 group. It will be called as a hyperchromic effect. Hypochromic effect. Decrease in the absorption intensity, that is decrease in the molar extinction coefficient, will be called as a hypochromic shift. It may be due to effect of solvent or oxychrome. For example, trans-cinnamic acid, which is more stable as per the structure is considered, then it is having epsilon value of 15,900. Same cinnamic acid, if it is in the cis form, then it will show decrease in the absorption intensity due to the cis conformation and epsilon value for this is 10,700. So there is a decrease in the absorption intensity, decrease in the epsilon value, hence it will be called as a hypochromic effect. So if you want to summarize, then we can say that bathochromic shift or red shift. So there is a shift of lambda max towards the longer wavelength region. Hypsochromic shift, lambda max shifts towards the shorter wavelength region called as a blue shift. Hyperchromic effect, there is an increase in the absorption intensity. It will be called as a hyperchromic effect. Decrease in the absorption intensity, it will be called as a hypochromic effect. So these are the questions for the practice. Definition of these different terminologies, then theory of electronic transition. Thank you.